Welcome to Easy Driver, the most reliable source of automotive information on YouTube. Please like, share, comment, and subscribe. Your car isn't just a machine anymore, it's a piece of software on wheels. This shift means updates, delivered wirelessly, are changing how vehicles get safer and gain new features. Over-the-air OTA updates are already common, but delivering them reliably across millions of cars is a huge technical challenge. For major Japanese automakers like Toyota, Honda, and Nissan, stability is critically important. They are known globally for their quality and reliability, and poorly handled software updates could damage that reputation. As 2026 approaches, regulations and consumer expectations for connectivity are growing. We're going to look closely at the stability frameworks these companies are building right now. These systems aren't just about successful downloads. They focus on guaranteeing the update process won't brick a car or compromise safety. Understanding these frameworks shows us how Japanese engineering will maintain its high standards in a software-driven future. What makes OTA updates go wrong in modern vehicles? While over-the-air OTA updates promise convenient improvements for your car, the process is far more complicated and risky than updating a smartphone app. Cars rely on many interconnected electronic control units, ECUs, that manage everything from entertainment to braking. Introducing a software flaw or interrupting an installation can lead to serious malfunctions, turning modern vehicle technology into a liability. Understanding these failure points shows us why rigorous stability frameworks are absolutely necessary. We cannot risk a connectivity glitch leaving a car inoperable or unsafe. The danger of incomplete or corrupted installation files. The most common reason an update fails is due to an interruption during the data transfer or installation phase. Think about what happens when you download a large file at home and your internet suddenly drops. The file becomes corrupt and unusable. In a car, this problem is far more critical because the installation often involves reprogramming the vehicle's core operating systems. Installation interruptions can happen for several reasons. Poor cellular signal. Updates occur over cellular networks. If the car drives through a tunnel or a remote area during the download, the connection can drop, stopping the file transfer midway. Low battery voltage. The installation process demands significant sustained power. If the driver begins the update with a low battery, or if the car enters a power-saving mode before completion, the process halts. User error. Sometimes a driver might mistakenly turn the car off or open a door at the wrong moment, interrupting the system while it is actively writing new software to an ECU. When this happens, the car's system can end up in a non-functional state. The system may only hold partially rewritten code. This results in a bricked system, essentially making a component, or even the entire vehicle, unusable until a technician can manually restore the software. This is a huge inconvenience, causing tow bills and lost time instead of the promised benefit of seamless updates. Why software bugs can stall critical car functions? Even if the update successfully downloads and installs, the software itself might contain defects, commonly known as bugs. We manage minor glitches on our phones daily, but in a vehicle, a software bug can have dramatic and immediate safety consequences. Car software manages essential life-saving features far beyond what your phone handles. Engine management. Bugs in this area could affect fuel injection, preventing the car from starting or causing it to enter a reduced power mode. Advanced driver assistance systems. This includes features like automatic emergency braking or lane keep assist. A simple programming error can lead to these critical systems misfiring, disabling them when needed, or activating them inappropriately. Infotainment and navigation. While less critical, bugs here can still affect the driver experience, causing maps to freeze or the backup camera to fail. The potential for faulty code makes extensive testing a non-negotiable step before release. Companies must deploy sophisticated stability and validation frameworks to catch these errors. Unlike a phone update, which is usually reversible, a faulty car update can disable core functions. This requirement for perfection directly drives the need for the robust Japanese stability frameworks we are seeing develop today. Japanese automakers' strategy for rock-solid OTA stability by 2026. Japanese automakers understand that their reputation for quality hinges on perfect OTA delivery. They cannot afford reliability issues or bricked cars caused by faulty updates. By 2026, their stability frameworks will rely heavily on specific hardware and software architecture choices designed to eliminate nearly all update failures. These strategies focus entirely on minimizing risk and guaranteeing that the vehicle keeps working, even if the update process stalls. Their goal is pure redundancy and rigorous stress testing before the software ever touches a public car. The importance of A-B partitioning for safe rollbacks. Imagine your car's main computer has two identical hard drives labeled Partition A and Partition B. This is the simple concept behind A-B partitioning, which is foundational to extremely stable OTA updates. Usually, the car runs all its systems from Partition A. When an update arrives, the car downloads and installs all the new software onto Partition B, which is completely inactive. This means the installation is happening entirely apart from the running system. Here is why this is a key stability measure. Zero downtime. The main system on Partition A keeps running normally while the update happens in the background. Drivers can often continue using the car during the download phase. Instant rollback. If the installation on Partition B fails, gets corrupted, or proves buggy during verification, the system simply ignores Partition B. The car continues using the proven old software on Partition A, guaranteed recovery. If the update on Partition B finishes loading, but then causes the car to crash or fail to boot, the bootloader automatically detects the failure and instantly switches back to the last known good version on Partition A. This switchback capability is critical. It ensures that a software bug or connection failure cannot leave the vehicle in an inoperable state. It is like having a perfect, non-erasable backup ready to go instantly. This redundancy significantly boosts customer confidence in the entire OTA process. Advanced pre-deployment testing and simulation labs. Japanese manufacturing is globally recognized for its commitment to zero defects. This same philosophy is being applied with enormous rigor to software stability through advanced testing environments. Before an OTA update reaches even a single beta tester, it must pass through sophisticated simulation trials. By 2026, many Japanese automakers plan to expand their use of digital twins. A digital twin is an exact software-based replica of a specific vehicle model, including all its electronic systems and microchips. The testing process in these labs is intense and highly focused. Extreme stress testing. Engineers simulate real-world conditions that typically cause updates to fail, such as sudden power loss, extremely weak cellular signals, or running the update while other high-demand systems are fully active. Environment replication. Simulation labs recreate the specific electrical characteristics, temperatures, and data bus loads of every component in the car. This ensures the update reacts exactly as it would in the physical vehicle. Comprehensive validation. They run the update hundreds or thousands of times on these digital twins. They check for unexpected memory corruption, timing issues between various ECUs, and potential conflicts with existing code. This process eliminates the vast majority of software defects before release. Using comprehensive digital twins means they can test failure scenarios that would be too costly or dangerous to replicate using physical test cars. This proactive approach supports the high reliability standards customers expect. That's the overview of how Japanese car makers are approaching OTA updates. Stay tuned for Part 2. Please comment, like, share, and subscribe for more automotive information like this. Thank you for watching.